What is the concept of wave-particle duality?
The concept of wave-particle duality suggests that particles, like electrons and photons, can exhibit characteristics of both particles and waves. This means they can behave as discrete particles with well-defined positions and momenta, while also displaying wave-like behaviors such as interference and diffraction. It challenges the classical notion of distinct particles or waves and is a fundamental principle in quantum mechanics.
Who proposed the wave-particle duality concept?
The wave-particle duality concept was first proposed by Albert Einstein in 1905, as he explained the photoelectric effect. He suggested that light consists of discrete packets of energy, called photons, behaving like particles. Later, in 1924, Louis de Broglie expanded this idea and proposed that particles, such as electrons, also exhibit wave-like properties. This duality challenged the classical understanding of particles and waves as separate entities. The work of Einstein and de Broglie laid the foundation for quantum mechanics, revolutionizing our understanding of the microscopic world and leading to significant technological advancements.
What experiments led to the discovery of wave-particle duality?
The experiments that led to the discovery of wave-particle duality include the double-slit experiment and the photoelectric effect. In the double-slit experiment, the interference pattern observed when particles or waves pass through two slits demonstrated the wave-like behavior of particles. The photoelectric effect, where electrons are ejected from a material by light, provided evidence for the particle-like behavior of light. These experiments played a crucial role in establishing the concept of wave-particle duality in quantum physics.
What is the double-slit experiment?
The double-slit experiment is a classic physics experiment that demonstrates the wave-particle duality of particles, such as electrons or photons. It involves shining a beam of particles at a barrier with two small slits. Behind the barrier, a screen or detector captures the pattern formed by the particles that pass through the slits. Surprisingly, the particles create an interference pattern, similar to the pattern created by waves, indicating their wave-like nature. This experiment highlights the intriguing nature of particles, behaving as both particles and waves simultaneously.
What is the interference pattern observed in the double-slit experiment?
The interference pattern observed in the double-slit experiment is a series of light and dark bands on a screen or detector placed behind the slits. It consists of regions of constructive and destructive interference. Constructive interference occurs where waves or particles from the two slits meet and their amplitudes add up, resulting in brighter or more intense bands. Destructive interference happens where the waves or particles cancel each other out, leading to darker or less intense bands. The pattern is a characteristic feature of wave interference and provides evidence for the wave-like nature of particles.
How is the interference pattern affected when only one slit is open?
When only one slit is open in the double-slit experiment, the interference pattern disappears, and a simple diffraction pattern is observed instead. Instead of having distinct light and dark bands, a single-slit diffraction pattern consists of a central bright region called the central maximum, surrounded by alternating light and dark fringes that gradually decrease in intensity. The absence of a second slit means there is no possibility for interference between multiple waves or particles, resulting in a diffraction pattern that is characteristic of a single source. This observation confirms the role of interference in creating the distinct interference pattern seen with both slits open.
What is the photoelectric effect?
The photoelectric effect is a phenomenon where electrons are ejected from a material when it is exposed to light or electromagnetic radiation. It occurs when photons, which are packets of light energy, interact with electrons in the material. The energy from the photons is transferred to the electrons, enabling them to overcome the binding forces and escape from the material. The photoelectric effect played a crucial role in understanding the particle-like nature of light and contributed to the development of quantum mechanics.
How does the photoelectric effect support the wave-particle duality?
The photoelectric effect provides evidence for the wave-particle duality of light. The observation that electrons are ejected from a material when exposed to light implies the particle-like nature of light, where light energy is transferred to electrons as discrete packets or quanta called photons. However, the photoelectric effect also exhibits wave-like characteristics, such as the dependence of electron emission on the frequency of light, rather than its intensity. This supports the wave-particle duality, showing that light can exhibit both particle and wave properties.
What is the Compton effect?
The Compton effect, also known as Compton scattering, is a fundamental phenomenon in physics that occurs when high-energy photons, such as X-rays or gamma rays, interact with electrons. During the interaction, the photon transfers some of its energy and momentum to the electron, causing a change in the wavelength and direction of the scattered photon. This effect provides direct experimental evidence for the particle-like nature of photons and supports the concept of wave-particle duality in quantum mechanics.
How does the Compton effect provide evidence for the wave-particle duality?
The Compton effect provides evidence for the wave-particle duality of photons. By observing the change in the wavelength and direction of scattered photons during their interaction with electrons, the Compton effect demonstrates that photons possess both particle-like and wave-like properties. The scattered photons' behavior can be explained by treating them as discrete particles that undergo collisions, transferring energy and momentum to electrons. This experimental observation supports the concept of wave-particle duality, illustrating that photons exhibit characteristics of both particles and waves.
Just as the wave-particle duality lies at the heart of quantum mechanics, so does the concept of wave-particle duality lie at the heart of all particles. Louis de Broglie.